Hi, welcome back. So in this last video, we will just cover what is sample proportion and the confidence interval of sample proportion. So the reason why we also have another sampling method, which is called the sample proportion, is because sometimes you don't want to test the mean. You want to test some other statistical measures. So one of the very useful measures that you can also test is proportions, and you'll be surprised that there's a lot of examples in real life that is kind of like proportion yes or no kind of questions, like for example whether you vote to a certain party or not, whether or not you are higher than a certain height or not, or whether your weight is overweight or normal weight, and so on. So whenever you have this kind of two options kind of sampling, then what you would use is the sample proportion instead of sample mean. So basically what I said was that a lot of real life examples are kind of two value. So those involves only the proportions. So whenever you see those kind of measures or samples, then basically you will use sample proportion. So the proportion for a certain statistic is given by x over n. So whereby your x is the number of success, and then the n is the total number of your samples. Okay. So your p hat is what we call as a sample proportion. So usually of course what we would use is to use the binomial distribution to study the statistics of sample proportion. So this means that what we are using is basically n and p, these two parameters. So from the binomial distribution, we know that the expected value would be n multiplied with p. The variance of x would be n multiplied with p and then multiplied with q. So q is your failure rate, so which is written by 1 minus p. So now let's look at the expected value of sample proportion. So the formula given above is x divided by n. So we know from previous chapters that you can move out your n, and that will give us e to the power of x, and then e to the power not e to the power of x but ex. So from the formula for binomial distribution, you know that ex is np, so you have 1 over n multiplied with np. So that gives you p. So it means that for sample proportion, the mean is just your probability of success, or the proportions. Now let's look at the variance of p hat. This is the variance of x divided by n. And for variance, when you move out the n, it becomes 1 over n squared. And then there is this variance of x. So the variance of x is npq. So you have 1 over n square npq. So in the end, you will have pq divided by n. So that is the formula for your expected value and the variance for your sample proportion. So previously, we also learned the definition of central limit theorem. It tells us that whenever your binomial distribution has a very large sample, it actually approaches to normal distribution. So the constraint is basically when, so this is just a guideline, when np is greater than 5 and q is greater than 5, then your sample proportion can be instead be approximated by a normal distribution, whereby the mean will be p, the variance will be pq divided by n. So this is very important because this allows us to find the confidence interval. So previously we also derived how would you find your confidence interval. So in this case, it is the same thing. So essentially you start with the first equation. You want to find the probability of p hat between a and b. Then you convert to z-score. So now instead of this part is sigma divided by square root n. This is square root of pq divided by n. And this will become p. Then you do all the same procedure in the end, and you will arrive with a very similar formula. So I don't bother to derive it because the procedure basically is the same. So the confidence interval is given by p hat plus or minus c. So c depends on your percentage of your confidence interval, multiply with the square root of pq divided by n. So the square root of pq divided by n is the standard deviation for sample proportion. So you just compare between these two. They are almost the same. You measure from the sample plus or minus your standard deviation of the sample. So in this case, this is sigma divided by square root n. In this case, this will be square root of pq divided by n. So basically, that's all you need to know for sample proportion. So let's look at two examples. So let's say you have a bias coin. You flip 500 times, and the result is the tail being 272 times. So part A, find the 90% confidence interval for the probability of getting a tail. Okay, let's do this. So you know that p hat is given by In this case, 272 divided by 500. So you can calculate this. This is 0.544. Okay. So then from the equation, you know that the expected value of p hat in this case would be 0.544. The variance of p hat would be 0.544 multiplied with 1 minus 0.544, and then the whole thing you divide by n, which is 500. So you calculate this, you get 0.000496. It's a very small number. So that is your first step, finding out the expected value and the variance. Second step is to find the corresponding C value when your confidence interval is given by 90%. So from our previous examples, so if you remember what we did from the last video, basically you are having the probability of z-score from minus C to C is given by that particular confidence level. So, and then you can sort of like simplify into 2 times P z smaller than C minus 1 equals to your confidence level. So in this case, we are doing the same thing. So this is 90% confidence interval. So we use 2 times Pz smaller than C minus 1 equals to 0.9. So you simplify everything. This will be 0.95. And when you read from your table, that will be 1.645. So that is your C value. Therefore, your 90% confidence interval is given by 0.544 plus or minus 1.645 times the square root of 0.000496. Okay, so in the end you will get something like this. So that will be your 90% confidence interval. So now let's look at part B. So this experiment is carried out 10 times. So how many of the confidence interval would be expected to contain the population proportion of obtaining a tail? So the answer is quite obvious, it's 9 times. That is the definition of confidence interval. So if you are using 90% confidence interval, you just use 90% times 10 and you will get 9 times. So let's look at another example. In order to test A six-sided die was fair. It was rolled 150 times. And 42 falls were recorded. So you have 1, 2, 3, 4, 5, 6. 4 recorded 42 times. So part A, find the sample proportion, which is your p hat. So this is simple. P hat definitely is just 42 divided by 150. So this is 0.28. So question B. What would you expect the proportion to be so that the die is fair? So this is also simple. P should be 1 over 6 if let's say this is a fair die. And 1 over 6 is roughly 0.1667. Part C. Find the 95% confidence interval of P hat. So in this case, what you need to do is to identify few things. So the expected value of P hat basically is 0.28. The variance of P hat would be 0.28 times with 0.72 divided by 150. So I did not actually calculate that, so let's leave it as a fraction for the moment. So 95% confidence interval, you can just directly plug in the formula as before. Pz, 2pz smaller than c minus 1 is 0.95. So pz smaller than c is 0.975, and you find that c is 1.96. So the 95% confidence interval is given by 0.28. Yep. Plus or minus 1.96 times your variance, the square root of your variance. 0.28, 0.72 divided by 150. So this is 0.21, 0.35. So that is your 95% confidence interval. So finally, part D. Based on your answer in C, is the die fair, sorry. So the answer would be no, because 0.1667, which is the requirement for you to expect the die to be fair, this particular value is not within the 95% confidence interval. So your confidence interval is somewhere around 0.21, 0.35, and in order for it to be a fair die, it has to be 0.1667. So it is outside of the confidence interval. That's why the die is not a fair die. If let's say you have a value in between, sorry, I quoted the question wrongly. If let's say this is your confidence interval, so then because 0.1667 is inside your confidence interval, so basically there's no evidence for you to reject the claim. So you can say that the die is fair. So more or less that's how you would test a claim using confidence interval. You look at the particular value that you want to test, and then the confidence interval, whether it falls into that or not. If it falls into that, then you don't have any evidence to reject the claim. But if let's say it is totally outside of your confidence interval, then you have the reason to reject the claim. If let's say you have to be inside that particular value. So that's the basis of testing with confidence interval. So that's all for this video, and that's all for the S2. So probably next week or in the next video I will try to cover back P2, P3, and then finally P1 and S1. Alright, thank you.